Okay, so thank you very much for the invitation to speak here. This is my first time in Russia, actually. And so what I want to talk about today is all joint work with Nick Wormold from Monash, and it concerns a topic which really sits, I would say, at the intersection of classical random graph theory, random regular graphs, and, say, random greedy algorithms. Sorry? Okay. So let me remind you here what the classical model is in this context, because I know we have a very diverse audience. So here I want to look at Aldous-Raney random graph, but in a sequential way. Okay, so the way I want to think about it is we start with an empty graph on n vertices, and now we step by step always want to add a new random edge to the graph. So situation looks here initially that we have this empty graph with these vertices, and then we want to step by step add new random edges to the graph. And for the purpose of this talk, it will not matter if we sample these edges with or without replacement, or in fact, if instead of sampling random edges, you just choose two random vertices and pretend that they're the end vertices of your edge. So we're interested here in the typical properties of these graphs, say, for example, the component structure after linear number of steps when the number of vertices is large. Okay, so it's not so easy to make statements about the random graph with 10 vertices or 20 vertices. We're all interested in what really happens when these guys get large. And one of the most interesting phenomena that you can, or I find one of the most interesting phenomena here is the phase transition in the component structure of your graph. So remember, we start off with an empty graph on n vertices. So initially all components have size 1. And now we start adding more and more edges to the graph. For a while, what will happen is that all the components will still stay relatively small. Say we're here on this left-hand side, where all the components stay at most logarithmic in size. But then, as we start adding more and more edges, there's going to be some kind of special point where if we add just a few more edges, and what I mean by just a few more is like epsilon n edges more, then the situation completely changes. So we're no longer in a situation where all the components are small, but one big component emerges, which kind of dominates the graph in the sense that it contains a constant fraction of all vertices of the graph, and all vertices outside are again small. Okay, so this is kind of the way I like to informally think about the phase transition phenomena, that there's a certain point around which adding just a few more edges completely changes the picture, the size and the structure of the largest component. So this is, of course, just some informal idea to keep in mind. If we want to talk about a little bit more formally, then here's maybe one way to state a very basic form of the Aldous-Raney phase transition, which intuitively says that this kind of dramatic change happens after roughly n half many steps. So one way to think about it is, okay, let's fix some t, which in this case is smaller than 1/2. Then we can show that with high probability, meaning with probability tending to 1 as the number of vertices tends to infinity, the size of the largest component will be at most logarithmic in size. So we're basically on this picture on the left. And if we take some fixed t larger than 1/2 and we look at the size of the largest component, then we know that the largest component is concentrated around some deterministic function times n, which will be of linear size. And the second largest component is again much smaller. All the guys outside here will be at most logarithmic in size. Okay, so this is one very basic way to state the basic Aldous-Raney phase transition. Nowadays, we of course have a much better understanding. We know very precisely here how all these constants depend on t. We know how does this function behave if we look at, say, t equals to 1/2 plus epsilon. We can even allow epsilon to be a function of n. So basically, we know almost everything about this particular phase transition. And the topic that I want to discuss today is not trying to study this model in more detail, but rather to try to establish a similar result for a more complicated random graph model. And now, of course, the question a little bit is, what kind of models should we study? And so sometimes I like to go back to some very early papers from Aldous and Raney, which I think are not so well known, surprisingly. So here's in particular one paper from 1961, which I like a lot because it contains some interesting quotes. So the Aldous-Raney model has been, say 20 years ago, a lot criticized for not being a realistic model. If you actually look into this paper from 1961, then you see that, of course, Aldous and Raney were already fully aware of this idea. So to quote from their paper, if one aims at describing a real situation, our model of a random graph should be replaced by a more complicated but more realistic model. Okay, so already in the 1960s, they already put out there, yes, if you want to really do real network modeling, then you should look at a different model. A-Ranee is not the right thing to look at. Furthermore, and this is what I like a lot here, they already put forward the idea, let's not just look at static random graph models. So what I mean by a static model is that, well, you tell me, please give me the random graph, and I present it to you in one go. But they emphasize the idea, let's look at time evolving random graphs, so graphs that build up sequentially over time. And why I like that is I think because the many real-world networks that we actually look at also evolve over time. If you think about Facebook, if you think about road networks and so on, all of these have some kind of dynamic aspect to it. It's not just you say, okay, please give me the road network and you build all the streets at once, but you really incrementally build them up. And so in this paper from 1961, basically what they said is, okay, if we want to sequentially add edges, one nice idea would be to say, okay, let's look at, suppose, what is the probability that we should connect, say, two vertices Vi and Vj in the next step? So basically we're asking, what is the probability that we join these two edges in the next step? And their suggestion is they should depend on the degree that these guys have in the current graph. So these are, say, the neighborhoods, and the sides of these sets here correspond to the degrees. And what they propose is the probability of adding this edge here in the next step should be proportional to some function of the degrees. Okay? And what we want to discuss today is kind of the simplest possible instance of this model, where we just say, okay, let's just forbid creating vertices of degree larger than d. So in other words, as soon as one of these vertices here has degree d, you assign probability 0 to this edge here. Okay? And this actually gives you exactly this random d process, which we can also describe like this. We start off with an empty graph on n vertices, exactly like A-Ranee. Again, we want to sequentially add random edges to the graph, but now we have the extra constraint. We have the extra constraint here that the maximum degree should stay at most d after you add this edge. Okay? So in other words, you only add edges which do not violate this maximum degree constraint. So let's maybe look at a small example of what's going on. I think then it will become very clear. So here, let's just focus for simplicity on the case d equals to 3. So here out there are red edges. And we're going to distinguish two types of edges, as you see in a moment, active vertices and inactive vertices. So active vertices here will have red. They have degree at most 2. They mean that we can still connect edges to them. And then we have inactive vertices. Those are of degree 3. And we call them inactive because you can no longer connect edges to them. They're kind of out of the game for the purpose of this process. So let's look at an example. So initially the graph is empty. We start adding more and more edges. And now you see that, for example, here this vertex of degree 2 has been created. And as it happens here in this example, the next step we connect another edge to this vertex. And now this vertex has degree 3, so it's out of the game. It becomes inactive. We can never, ever connect something to that. And so on and so forth. And now basically for this kind of random graph model, we can ask exactly the same kind of questions we also can ask for the classical A-Ranee model. We can ask for, okay, what about a giant component, and so on and so forth. I should say that for most of what I'm saying today, there's a different way to describe this D process. So another way to think about it is, and really for most of what I'm saying it will be the same, in each step just select 2 active vertices and connect them by an edge. This says there are a few minor differences here and there, but believe me, any result you prove for one, you can transfer to the other. Okay? So let me say 1 or 2 words about this model. So one is if we put kind of some trivial degree constraint on each maximum degree constraint, then we cover A-Ranee. So if we set d equals to n, or in fact n minus 1, well then we effectively have no constraint on the degrees, so we're just adding purely random edges. So this model here contains A-Ranee as a special case. Furthermore, we can study a variety of different variants of this process. So nobody forces us to say that every vertex should have the same maximum degree d. Could be that some vertices can have degree 2, some can have up to degree 3, others up to degree 4. So we can also study such variants, but I'll not discuss them here in this talk. Similarly, we can look at hypergraph variants, where each edge, instead of containing 2 vertices, can contain k vertices. Okay? And we also have results on these models, but let's, for the purpose of this talk, let's try to keep everything here in the deregular case. One thing I'll try to emphasize more on the next slide is that this model differs from the usual configuration model that you might know for generating random deregular graphs. So it actually turns out that this particular process, so this is a result by Ruchinsky and Wormald from the early 90s, actually with high probability gives you a deregular graph modulo some vertices which you cannot cover due to parity constraints. Okay, so, but I'll mention this a little bit more on the next slide. So now that you've seen the model, I think it's a good time to step back and ask for motivation. So why do we care besides that maybe it's a nice mathematical model? So, so the first thing I want to highlight here, at least for me, this is an extremely natural model to try to generate deregular graphs. So I'm pretty sure, for example, if you try to give it as an exercise to undergraduate students, try to generate me a deregular graph or a random deregular graph, that this is one of the first things I think that they would try to come up with. You just greedily put in as many edges as possible without violating this degree D constraint. This configuration model that we now know, maybe it's not the first thing you write down because it's kind of specifically tailor-made so that certain probabilities are uniform. So in fact, if you go in the literature, this model has been studied or was proposed in the 1980s in the context of some mathematical chemistry literature. So it has been studied for quite a lot. Another thing I like about this particular model here, maybe I should highlight this here, is that it again contains this time evolution aspect. So many times when we try to model certain things by networks, the question kind of is how much information do we take into account? So a very popular approach is, for example, to focus on the degree sequence, then to say, okay, we take a degree sequence as a very significant characteristic of the network, and then we observe the degree sequence in some model, and then we make predictions just based on the degree sequence. But you kind of, when you do that, ignore the fact that maybe your model arrived at this degree sequence via some time evolution. I think if you think about modeling things like a road network, then it becomes very evident that maybe you can think of a road network as being a planar graph. Okay, so you could imagine, let's just model as a random planar graph. But clearly this can potentially ignore the fact that you arrived at your road network by incrementally building a road here and there. And then the question is, do you get different properties if you do it in this dynamic way versus this just taking a random planar graph? A second motivation for this here is maybe more of a technical nature. So there's this very influential survey by Nick Wormald from 1997, which discusses in great detail how to use the so-called differential equation method for understanding the behavior of certain random graph processes. And in particular, he asked about the existence of the phase transition in this random D process in that paper. And I think this was one of the last open problems left over from that survey. And finally, there's another kind of, maybe for me, the most important motivation here is that, we have a very good understanding of various random graph models like A-Ranee and also the configuration model. We can analyze them in great detail because we can somehow represent them as a sequence of independent random choices. And once we are in the situation, we have very, very strong tools and techniques to analyze them in great detail. When you look at things like the random D process, then the dependencies become quite delicate. So one way to maybe see this is that you can only add kind of edges between vertices that are still active. And the set of active vertices kind of changes over time, and this kind of makes a lot of the standard tools and techniques unavailable in this setting. So it's kind of like a test bed for development of new tools for studying the phase transition. So let me tell you one or two things what is known here from a mathematical perspective. So a lot of the combinatorial emphasis has been on the final graph itself. So, for example, I mentioned this result by Ruchinsky and Wormald. They showed that with high probability the final graph is deregular for D at least 3, and they also showed it's in fact connected. So, for example, the fact that the final graph is deregular, this was answering a question of Erdős from the mid-80s. And there has been also some very interesting work for the special case d equals to 2, where they study things like subgraph counts, like what is the expected number of triangles in this model. And they also studied what is the probability that your graph is Hamiltonian, that it consists of one long cycle. And these results, I should say, I find them quite remarkable. For example, the probability that your graph is Hamiltonian is something like 1 over square root n. And they even managed to nail down this probability up to the constant there. It's really quite remarkable results here. So what is the problem that I want to discuss? Just to be sure, we want to discuss this phase transition phenomena. So when does this linear sized giant component emerge? And the key question is, can we kind of find a deterministic point where the giant component emerges? So just to be sure, so in this talk often I'll write things like I is equal to t times n steps. So this is a convenient renormalization, so we can kind of think of t as being time. And for later, let me just recall, so Li will usually be the size of the largest component. Okay, so, and the question is there a deterministic time t where the giant component emerges? So in A-Ranee, we saw after roughly n-half many steps the giant component emerges, so the critical time would be tc equals to 1/2. And the question is, does such a time exist in this process? As a first attempt to solve this problem, let's do kind of a thought experiment. So let's just, as a thought experiment, think of that we stop the process after a certain number of steps, say t times n many steps. Right? Then we can observe how many vertices are there of degree 0, how many vertices of degree 1, how many of vertices of degree 2, and so on and so forth. And then we can attempt to use a widely used heuristic, which basically tells us, okay, once we know the degree sequence, we should be able to predict whether there's a giant component or not. Okay, so this is in other words, we're asking the question, does a random graph with this degree sequence have a giant component? And there's a very well-known criterion for when a random graph with such a degree sequence has a giant component. It's the so-called Molloy-Reed criterion. I think in the next talk, Bruce Reed will tell us a little bit more about that story. For the purpose of our talk, there's a very well understood criterion here. Intuitively, it corresponds to some branching process condition. And so we can, once we stop the D process, we observe the degree sequence, and then we can query, would this Molloy-Reed criterion tell us whether there's a giant component or not? Okay, this is kind of one heuristic way to approach this question. And if you do that, it turns out that the answer you get this gives you kind of the wrong answer. So what I mean here, if you just use the degrees to predict the location of the phase transition, you get a different answer. So here, if you say using simulations, observe when does the phase transition happen in the D process. For D equals to 3, maybe it happens after 0.577 steps. If you use this Molloy-Reed approach of observing in each step the degree sequence of your model and asking, would Molloy-Reed tell me whether there's a giant component or not, then you would see that this would only kick in later at 0.578 steps. Okay, so in other words, it's an example where we need to be very careful when we apply these heuristics, and moreover, it's an example where the dynamics of the process really affects a key quantity here. So in this case, it really alters the location of the phase transition.
Even though it's not very far off, right?
Yes, but it's still different, yes. I mean, I should say that this approach is not too crazy. For example, in some recent joint work with Svante Jansen, it turned out that in such a dynamic model, once you condition degrees, you exactly get the uniform model back. It was very surprising, but sometimes it actually happens that once you condition on the degrees, you're back to the configuration model. Okay. So once you study this process in simulations, the D process, then you very quickly see that as D gets larger and larger, well, you very quickly approach 1/2. Okay. So the relevance of 1/2 is that it's the same phase transition location as A-Ranee. And we can also kind of explain or intuitively explain why that's the case. Okay, so basically what I want to now do is I want to convince you that kind of finite D or small d is the most interesting case to study. And so to do that, let's recall ourselves. So on the one hand, we have this A-Ranee process which just adds random edges to our graph. On the other hand, we have this random D process, which you can think of in a similar way as A-Ranee, just that every now and then it rejects edges, which will create a vertex of higher degree. Okay, so we have uniform process here, and this D process, which kind of rejects certain edges that create vertices of high degree. And now the key point is that in the A-Ranee random graph, the linear number of edges, the number of vertices of degree larger than D drops off exponentially. So the number of vertices of degree larger than D, if you just make D large enough, will be something like at most epsilon n. Okay, so in other words, if D is very large, the number of vertices with degree larger than D is tiny in A-Ranee. Okay, so now we have this A-Ranee process, which kind of puts down just random edges and creates a tiny amount of vertices of degree larger than D. This, on an intuitive level, at least indicates that this A-Ranee random graph and this D process should behave very similar. And there are ways to make this kind of comparison argument I just described rigorous. There are ways to really make that, say that, okay, this is really actually a rigorous mathematical argument. In fact, one can squeeze out even more. So here what we looked at is fixed D, and then we let D tend to infinity. If you do the same argument where D is now a function of n, that just tends to infinity, so think of log n or whatever, then the same argument actually tells you that the critical time is exactly equal to 1/2 as in A-Ranee. Okay, so what this is trying to tell us is that for the kind of for our question of where the phase transition happens, we should look at only at finite D. That's where all the action is happening. So what is our first result here? So as I mentioned, this is joint work with Nick Wormold. So the first result considers D at least 3. And we can basically show that there is a phase transition that, if you look at it in this very basic way, looks like A-Ranee. So we again have some critical time Tc. If your t is smaller than this critical time Tc, we get logarithmic size largest component. Now, of course, the constants here can depend on D. But we again get logarithmic behavior. The size of the largest component here, this L1, it's concentrated around some deterministic function times n, which is of linear size. And the second largest component is again logarithmic in size. Okay, so up to these constants here, it's exactly the same way I phrased the basic A-Ranee result. And this solves this problem of Nick Wormold from 1997 in a very strong form. And
Do you have a clean form for T sub C of D? You just say there is a critical one.
So we also have a way to calculate in the sense, okay, so TCD is given as some blow-up point of a system of differential equations.
Yeah.
And we also have a rigorous mathematical argument. If you can approximate the susceptibility up to a certain precision, I can convert that into a rigorous bound on TC.
But T sub C of D itself is defined, can be rigorously defined as the blow-up point.
Yes.
Explicit system of differential
Uh-huh.
equations. That's explicit enough.
Yeah. And so if you would ask me, like, which is now the hardest of all these results to prove here on the slide, it actually turns out that the second largest component, that's logarithmic in n, that's actually the hardest argument here. And as it looks, we probably will split up the paper into two to make this a separate paper because it's quite technical. But it's really beautiful. It involves something like conditioning on the future of the process, but let me not say more about it. It's really nice. For the phase transition experts in the room, let me just mention that there's some work in progress where we also identify exactly what the growth rate of this function rho of D is. So similar to A-Ranee, we can show that you get some linear growth. So if you're epsilon away from the critical time, you have size roughly constant times epsilon, where the constant, of course, depends on D. And you can also show that as D gets large, you approach the A-Ranee constant. But this is also quite tricky. Okay, so now we discussed D at least 3. So what about the remaining cases I left out here? So, okay, D equals to 1. It's not such an interesting case, right? Because the largest component that you can get is 2. So with respect to the phase transition, this not so interesting. So what about the case D equals to 2? So it turns out that behaves a little differently. Okay, it's something interesting happens. So again, so maybe I should say that in the 2 process, you can add at most n edges to the graph. Okay. So the process runs for at most n steps, And what we can show is that kind of all the action happens at the end of the process. So if you look at, again, any fixed t smaller than 1, then the size of the largest component after t times n many steps is logarithmic in n. But then if you look at the largest component at the end, okay, after n steps, then the largest component is not concentrated. So if you look back on the previous slide, we said that with high probability for d at least 3, the large component is concentrated around some deterministic function. And here we see something different. So here we see that, so if you look at the probability that the large component size is bigger than constant times n, that's asymptotic to some function f of c, which lies strictly between 0 and 1. Okay, so you get some kind of a probability distribution. So it actually turns out that
But what about L2?
it will also be the same as also. Yeah, so if you look at largest component bigger than C1 and second largest component bigger than C2, this will be asymptotic to some function, again, depending on C1 and C2. Yeah. So in fact, we figured out that this question was for d equals to 2 was actually asked by in 1993 by Balinska and Quintas. So they were interested in the following question: what is the probability that your final graph has size at least n over 2? Okay, that's what they were interested in, and our result says that this is asymptotic to ln square root 2 plus 1. I think I made somewhere some notes what this is, but it's like, okay, 0.8814. Okay, and so this, that it has this asymptotics, this answers this question by that they raised in 1993. And you might wonder, how could they predict this thing so precisely? And so it turns out that the function f that we observe here in this 2 process is exactly the same function that you get for random 2 regular graphs. So if you look at random 2 regular graphs, they're basically a collection of cycles. And if you ask there the question, what's the probability that the largest component has size bigger than constant times n, you get exactly the same f of c. Okay, so in that sense, this 2 process behaves more like a configuration model, not like A-Ranee. Okay.
Is this like the cycle size of a random permutation?
You can basically mimic the same proof, and
which is well studied.
yeah, I mean, it does not yet explain why it comes in here in the 2 process,
Yeah,
but
the result is similar.
well, yeah. Somewhere in the proof you need something what you described, that you need to be able to how to actually calculate this f of c. But basically how this result is proved, as you're asking, if you kind of go very, very close to the end until you basically only have like a certain like paths of a certain length, imagine. And now if you look at how paths join up, right, only the endpoints of paths can be active. So it is, but yeah. But,
can you also couple the two, let's say, after adding n edges, couple the thing to an ring also a graphical configuration model, where you pair the n edges, or it doesn't?
You mean for the general, yeah.
No, for this particular setting, the 2 regular, like
Yeah.
regular case.
So you're asking, is it true that you can couple the 2 regular, for example, configuration model after so many steps with this model? I think coupling is a too weak notion to capture how close they are. So it is, for example, the expected number of triangles in the 2 process at the end and the 2 configuration model, they differ. But it's conjecture that they're still contiguous, these 2 models. So if you look at the final graph, they're contiguous. So I think total variation distance and so on is not a strong enough notion to. Okay, so are there more questions?
In your process, the D process,
Uh-huh.
I mean, to what extent are the final graphs, I mean, the configuration model is they're uniform, given that it's
So yeah, so okay, so the feeling is, so this is also, I should say, a conjecture of Wormald from the 90s, that the final graph of the D process should be contiguous to the uniform random D regular graph. but proving that is quite tricky. I think we had some hope that maybe after this result you can do it for 2, but it doesn't seem to be very easy to prove that. But the fact that the same function pops up was very encouraging here. Yeah. So I think the main difficulty in proving it somehow is that in the D process what happens is kind of all vertices look the same, and just if you have higher allowed maximum degree you can stay longer in the process. Whereas in the configuration model, if you have higher degree, there's like a higher probability of attaching to a vertex. And how to trade off these two things, it's challenging. Okay, so let me say a few words about the proof. Or I want to rather say something about the proof philosophy, maybe not so much about the proof itself. So here's one very nice key parameter I want to introduce. So if you don't care so much about all these proofs and results, here's maybe one nice concept that you can take home, that this is a useful parameter. So it comes from mathematical physics, and it's a so-called susceptibility. And it's basically the answer to the following experiment. So given some graph G, sample a random vertex from your graph and ask what is the expected size of the component that contains this randomly chosen vertex. This is exactly what we define here as the susceptibility. And it turns out that this is, with respect to the phase distribution, seems to be a very important parameter. So let's try to get some very, very basic intuition what's going on here. So let's do something crazy. Let's throw away almost all the information of the susceptibility for now and just focus on the largest component. So the largest component will have L1 many vertices inside it, and it will contribute here L1. So in other words, susceptibility, or at least the size of the largest component squared over n. Okay, so because up here, the largest component will contribute L1 many factors. So we get this nice inequality here, and that's already enough to get some intuition what's going on. Admittedly very rough, but some intuition. So imagine that you already have a linear size giant component, a component of size n. Then by this inequality here, the susceptibility will be of linear size, right? Because this is order n squared divided by n. So it'll be of linear size. So in particular, as n tends to infinity, it will diverge. Whereas, so in other words, the existence of a giant component implies diverging susceptibility. Whereas if you have a susceptibility that's still bounded, still finite, if you just look at this inequality the other way, it tells you that the largest component will be of order at most square root n. So in particular, it will be sublinear. So now we have this nice kind of trade-off. Linear size giant component, diverging susceptibility, finite susceptibility, sublinear size largest component. So maybe the point where the susceptibility diverges, maybe that actually coincides with the critical point where the giant component emerges. And I should admit, if right now this seems like an extremely weak heuristic. But there's more to it. So I should first mention that there's some motivation here by classical percolation theory on infinite lattices. So there, a priori, you have two different definitions of a critical point. One is the point where the expected cluster size at the origin is infinite, and the point where the probability of having infinite cluster is positive. And it's a very deep result in percolation theory from the 80s by Menshnikov and Eisenman and Barsky that these 2 points actually coincide. And in some sense, what we're doing here is we're kind of asking an analogon of this question in the setting of these random graph processes. Does the point where the susceptibility diverges coincide with the point where linear size giant component emerges? So take my word for it that one can check that this statement here is true for A-Ranee. It's also true for a bunch of other random graph processes, so-called bounded size Achlioptas processes. It's true. And as part of our proof, we also show that this is true in the random D process. So the point where the susceptibility diverges coincides with the point where the giant component emerges. And but it's kind of more like a consequence of our proof, okay? So it drops out as a consequence because somehow the susceptibility does not seem to be the right quantity because somehow, if you remember our process, only the active vertices matter. Somehow, once vertices become inactive, it's no longer relevant for the evolution of the process. We can never connect edges to it anymore. So we somehow need to look at something else. So how many minutes do I have left?
You have 9 minutes.
Oh, okay. So that motivated us to look at a variant of the susceptibility which takes into account which vertices are active. So let's denote suppose we denote the active set by A, script A here. Then it turns out that this is a good quantity to look at. We want to look at kind of the active susceptibility, which is the answer to the following question. Sample a random active vertex, and let's ask what is the expected number of active vertices in the component containing that randomly chosen vertex. Okay, so it's the same as above, just that we think of here we are just interested in active vertices and we just sample from active vertices. And it turns out that that's the relevant quantity to look at, which is clearly guided by the original susceptibility but different. Okay, so now we have this active susceptibility, and now we want to understand how it behaves. And whereas for A-Ranee you can write down, you can track it fairly easily. You don't need to introduce any further auxiliary variables. Here we run into a problem, because somehow you need to track a large number of variables in order to be able to recover this quantity. So part of the reason is because you need to know when vertices can become inactive. To know when vertices become inactive, you need to know when do they have degree d-1 already. But in order to know when do they get degree d-1, you would need to know when do they have degree d-2 and so on. So you need to know basically all the degree information about your component. Okay, so it turns out that you can track this thing, but you need to track order d squared many variables just to recover this one variable you're interested in. And if you don't look at, say, at the d process, but you allow for different degrees, then this goes up to d to the 4 actually variables. So, okay, so now we have this susceptibility here. We can track it using order d squared variables. And now we run into a problem because so the way many of these proofs work is that kind of you have these random variables you're interested in. Then you use some technical machinery that was developed by Nick Wormel, the so-called differential equation method, which is in statistical physics language also known as kinetic theory approach or rate equation approach. You can use that to track these variables. And the method basically tells you can predict the behavior of these guys using differential equations. But now we're left over with the question, when does this thing blow up? When does it get infinite? And at least for me, it's not so easy to analyze a large system of order d squared many differential equations. It's not so easy for me. And part of the difficulty is because some of the variables that you track turn out to be not monotone. So you want to show that something blows up where some of the variables inside are not monotone. It gets quite tricky. So we need to do something else. And one of the ideas that we decided to use here is, okay, let's try to kind of sidestep the question of showing directly that the system of differential equations has a blow-up point. Let's try to do something a little bit differently. And so one thing that we try to use here is the fact that we kind of turn this usual method on its head. Usually what we do is we try to understand the behavior of random variables using differential equations. And now we want to do it the other way around. We want to use the process to show something about the differential equations. So we kind of turn the usual methods on its head. And the reason, in a nutshell, why this ought to work is the following. Let me maybe see if I can try to explain. So, because usually what these arguments tell you is that after suitable rescaling, certain random variables converge in some sense in limit to the solution of a differential equation. Okay? And here we know that this differential equation must have a unique solution. So if there's a property of your random variables that's not reflected by this solution to differential equations, you would construct a second solution with these different properties, and that would contradict uniqueness. So the fact that you have this limiting object, which is unique, that allows you to transfer properties of the random process to these random variables. Because if they would not be reflected by the limit, then you could use the random process to construct a second solution which differs from the original solution you started off with. But okay, maybe this is a little technical, but the key idea is we can use this idea of the random process to analyze the differential equations. And the way this kind of works is something like the following. We don't really know exactly how to understand the behavior of the D process for a very long time, but maybe if we just need to understand a few steps, epsilon n steps, maybe we can say something very weak about the behavior of the process. And so maybe we can just say something, oh, maybe things don't go too bad in this short interval. Maybe we can, for example, still say that when we look at the random variables, the active susceptibility has not diverged yet. It's a relatively weak statement, maybe, but that would be good enough to say something in the end using this idea for the differential equations. Okay, so the idea here is we want to kind of use some very rough information about the graph and transfer that to the differential equations. And it turns out, interestingly, that for this purpose we can use some ideas that we developed together with Oliver Yoder in the context of so-called Archaeopteros processes. So there were some technical difficulties understanding these other processes, but the main point was somehow their differential equations were not available due to technical reasons. So we needed to find a way around using differential equations. And it turns out that there we developed a way to write certain proofs so that if you have a little bit of rough information, it kind of drops out for free that a certain other variable needs to diverge, which in this case means that your system of differential equations has some blow-up point. Okay, so it's kind of nice that something that we developed originally for sidestepping differential equations here allows us to feed back and show actually that if you have differential equations, you can still now get this blow-up point information without going through this complicated analysis of so many differential equations. Okay, so let's take a step back. So what was going on? Kind of the idea was we had this nice quantity motivated from mathematical physics, susceptibility, that guided kind of our proof to look at what is the right variable to look at. This was this active susceptibility. And then we kind of developed some technique which allowed us to sidestep the analysis of such a large system of differential equations, which seems quite tricky. Okay, this is all I really want to say here, so let me summarize. So we are looking at the phase transition in this random D process where we always add random edges without creating vertices that have to be larger than D. We saw these two different kinds of behaviors. For D at least 3, we basically saw this A-Ranee-like behavior. And for D equals to 2, we got this non-concentration, which was more reminiscent of this random 2 regular graph. And the key quantity here was this susceptibility motivated by mathematical physics. And I'll stop here. Thank you.